Okay, I want to welcome you to my lecture today. Of course, today we're starting a new topic that we call analysis of covariance. Before I go into today's topic, I think I need to tell you this. The midterm 2, we actually cover everything that we did from two-way analysis of variance up to this topic, up to the analysis of covariance. The analysis of covariance that we're starting today, we're going to finish it on Friday. So which means the midterm 2, we actually revolve around two-way, what we start from two-way analysis of variance all the way to analysis of covariance. So which means everything that we did from two-way up to this week, Friday. Let me specifically tell you this. There's going to be 4 questions in midterm 2. And one of these 4 questions will revolve around these 4 areas, which I'm going to mention now. Of course, there's going to be a question from two-way analysis of variance, whether with fixed effect or random effects and stuff like that. And of course, we actually also going to have a question from analysis of variance with blocking effects. Okay, analysis of variance with blocking effects. And of course, we're also going to have a question from analysis of covariance. So I'm going to send you a message today through an announcement section. You're basically going to see the areas that will be covered. And that is the reason why you need to be able to pay more attention from this time, of course, because what we want to start today will be part of midterm 2. Okay, so I want to welcome you once again to new topic that we call the analysis of covariance. Of course, the reading is taken from the chapter 17 of the recommended textbook. Now, in the outline, of course, I'm going to introduce you to the analysis of covariance. Then I'm actually also going to walk you through our example. Of course, the reason why I decide to put our example on my lecture slide is basically for you to be able to prepare, practice all the code even before your lab session. Okay, so I want to have an introduction now to the analysis of covariance. But let me tell you this, for you to be able to understand the analysis of covariance, you need to first understand the analysis of variance. I'm going to say this again. For you to be able to understand the analysis of covariance, you need to first demonstrate an understanding of the analysis of variance. Because when you look at the analysis of covariance, the difference between this and the analysis of variance is that co. Take a look at that. Now, let me also tell you this. Analysis of covariance, we can actually denote it as ANCOVA, or at times we can write ANCOVA. Okay, whether ANCOVA or ANCOVA, of course, they mean analysis of covariance. The analysis of covariance actually combines 2 techniques. The first technique is ANOVA. The second technique is regression. I'm going to say that again. The ANCOVA that we're talking about now, okay, the ANCOVA that we're talking about now, okay, is the combination of the ANOVA and regression. I know some of you have heard about regression analysis before. So because of this, I'm basically going to say ANCOVA is a generalization or an extension of ANOVA. Okay, I'm going to say that again. ANCOVA is an extension or a generalization of ANCOVA, of ANOVA. Okay, so the ANCOVA actually combine both ANOVA and regression. Now, I'm actually, I'll first start from an example, and that very example, we're first going to reason with that example as ANOVA until an introduction of something. Okay, now I'm going to give you an example now. Like I said, I promise I'm actually going to give my own example in class. Let's say, for instance, you are preparing for midterm 2 now, right? And I decide to, study the effect of 3 studying techniques. Okay, 3 study techniques, A, B, C. I partition the whole class into 3. I partition this class now into three groups, and I actually use a study technique A for group A study technique B on group B, and a study technique C on group C. And in the end, maybe after one month, I conduct exam, right? If I conduct exam and I basically want to compare the exam scores in these 3 groups, of course, I'm basically going to use a one-way analysis of variance. Exactly, that is what we've done before. Of course, one-way analysis of variance, a fixed effect, because I only have 3 techniques. But don't also forget, when I choose these techniques from a population of techniques, that actually become a random effect. Does that make sense? Okay, but let's say I'm interested in just fixed effects, or just because, I only have 3 techniques. Of course, when I conduct the exam and I'm comparing that, I'm basically going to use ANOVA for that. But let me tell you this. The only condition for me to use ANOVA for that is when you guys have not written any exam before. But if you have written exam before, just like you've written midterm 1 now, and of course you have seen results, and there's a variation in results, right? The results are not the same. Okay, if I want to introduce, okay, that's your current grade. Your current grade now is a covariate, because you know why? This particular maybe the reason why there's a significant difference between this group is because of your current grade. Before I can use ANOVA, okay, we got to make sure there is no any other covariate that could influence the response. I'm going to say that again. Before we can use analysis of variance, we're actually going to have an assumption. There's no any other potential variable that could influence the response. But in a situation where that exists, and when it exists, it has to be continuous, not categorical factor. Because if it is a categorical factor, then I'm not going to have ANCOVA anymore, but I'm going to have a 2-way ANOVA. Because study technique is one factor, right, with 3 levels. Then maybe another categorical factor will make it a 2-way. Okay, so what am I trying to talk about? The covariate that we're talking about is continuous, it's quantitative, it is not categorical. And that's exactly what I mean. On that page, when I said a covariate is a quantitative variable. But let me tell you this, that quantitative variable, initially, it was not of interest. That is not our primary variable of interest. Our primary variable of interest is the study techniques. But all what we just need to do is to adjust, okay, is to adjust, okay, for that covariate. Because let me tell you this, one of the worst enemy of statisticians, psychologists, sociologists, the worst enemy of scientific community in general is what we call bias. And when an important variable is missing in a model and you don't account for that, your model will induce bias. What is that important variable we're talking about? Covariate. So the addition of covariate, okay, into ANCOVA now, then makes it becomes what I call the ANCOVA, the analysis of covariance. Now, let me also tell you this. What do we mean by covariance? Oh, covariance actually means joint variability of variables, joint variability. That's what we mean by covariance. Joint variability. I want to award an extra credit now. When a covariance is standardized, what does it become? Can somebody tell me? When a covariance is standardized, what does it become? Oh my God, another extra credit, send message to me. When a covariance is standardized, it becomes correlation. Okay, now, we have so many examples of analysis of covariance. I think I just gave an example now. I put out so many examples for you, but I'm basically going to go into the ANCOVA example given in the textbook. Okay, the data are from Montgomery. Okay, now we want to assess the strength of thread made by 3 different machines. 3 different machines, right? Each thread is made from a batch of cotton, and some batches tend to form thicker thread than other batches. There's no way to know how thick it will be till you make it. Regardless of how the machines may affect the thread strength, thicker thread are stronger, of course we know, you know. Thus, we record diameter as well as strength, with diameter as a covariate. In this example now, because there's a diameter, okay, that need to be adjusted. The effect of diameter need to be removed before we can successfully, you know, investigate the effect of the factor here, or the effect of the machines, or on what, on the strength of the thread. If we don't do that, if we ignore that, then we're actually going to have an issue. Then it means our errors will be affected whenever there's a violation of assumption in statistical analysis. It will tell on the error. Error will be affected. When the error is affected, then you are no longer having an efficient result. I mean, model. Whatever recommendation from such model may not see the light of the day. And that is why it look at times as if our models are failing us. Our models are not failing us, but we are the one that we're not doing the right thing. Now, I want to investigate the effect of covariate now. Now, let me first tell you this. I told you on Monday, every statistical model has assumptions, right? I told you. I remember I told you a scenario. The moment you ignore assumptions, if assumptions are violated and you continue to use your model, you are more or less like a judge who tried a case in a wrong court. If a California judge should try a suspect that committed offense in Minnesota, even if the state of nature have it that the person commits the offense and the judge in the California was able to establish that fact, then whatever decision they make is null and void. The same thing also applicable to a doctor that did not do any diagnosis, a medical doctor that did not do any diagnosis, but eventually gave a right drug to the patient. I'm going to say that again. A doctor that didn't do any diagnosis, but in a way gave a right drug to the patient. Even though he gave a right drug, that only occur as a result of an accidental discharge of nature. That is not right. Okay, now, because ANCOVA that I talk about combine the technique of ANOVA and the technique of regression, then it means ANCOVA model we have more than the number of assumptions ANOVA have. There will be additional assumptions. All assumptions of ANOVA are still retained in ANCOVA, but we have few additional one. Number one, additional one, there must be relationship between the covariate and the response. I'm going to say that again. I'm talking about the ANCOVA assumptions now, and I said all ANOVA assumptions, okay, also go with the ANCOVA assumptions, but there's going to be additional assumption. Number one of that is there must be a relationship between the covariate and the response variable. And number two, there must not be relationship between treatment and the covariate. I'm going to say that again. The treatment is a factor, a categorical factor, right? No relationship should exist between the treatment that I call a categorical factor and the covariate. What am I talking about? In my example here, there shouldn't be any relationship between the study techniques and what? And the current grade. There should not be any relationship between them. But relationship should exist between the covariate, which is the current grade here, and the exam score. Does that make sense? Okay, now, if you take a look at what I have on the board, we're actually looking at the effects of machines on the strength, right? But we realize there's a potential variable, a quantitative variable that needed to be adjusted that we call diameter. And what do you think we're doing now? We're looking at the relationship. Is there a relationship between the response variable strength and the diameter covariate? If I want to investigate that, I will actually use a regression approach. Take a look at what you see on the board. LM model dot O. LM is a linear model. Then strength on diameter. The name of my data is EX. Then I do the ANOVA on that. When I do ANOVA on that, what am I trying to say? I'm interested in the p-value associated with the diameter. The p-value associated with the diameter here is very, very small. Okay, it's less than any reasonable level of significance. So what is our conclusion here? Relationship exists between the covariate and the response variable, and that now justify, using an ANCOVA. Okay, we can also go by way of that. We perform a simple linear regression, okay, technique on the response variable strength and diameter. And if you take a look at the p-value, of course, you're basically going to see there exists a significant, difference. So which means the covariate actually has a significant contribution to the response. But what of in a situation where the covariate does not have a significant contribution to the response? In that situation, we don't need ANCOVA. We only need a one-way analysis of variance. Take note of that. Now, of course, I know you are aware of a scatter plot. Okay, in linear regression, the scalar plot, we actually give a diagrammatical plotting of the response variable against the explanatory variable. The explanatory variable here is the diameter that's acting as a covariate. The strength is a response. As you can see, oh my God, this is a straight line. You can see the line of best fit. Most of the point, they are very close to this line. Of course, you don't expect all the points to be on the line because we've acknowledged the fact that we don't have a perfect model. Relationship exists here. Now, what is the next thing we're going to do? The next thing we now want to do now is to perform a linear regression technique, between the machine and, the response variable. Let me tell you this. What we can achieve with analysis of variance, we can also achieve that with regression. I'm going to say that again. At times when I check online, when some researchers or some people are trying to differentiate between regression and ANCOVA, I normally see there's a lot of this, misinformation, disinformation. You need to be able to don't rely on the source when you're getting information. Try to exploit. Somebody used to tell me, the difference between regression and analysis of variance is in regression, we use analysis of variance to compare groups. And why linear regression, we actually use that if you basically want to make a prediction. That is not true. What we use analysis of variance for, we can also use linear regression. But what is the difference between the two? We use regression when you are, working on observational data. Observational study is the one you get through survey, or you are working with historical data. But analysis of variance, on the other hand, we use that on experimental study. Experimental study is the one, where you actually partition participant into group using the principle of randomization. And that is the reason why experimental study actually has more statistical power than the observational study. So if you take a look at what I'm displaying now, this is a linear regression where we are looking at effects of an explanatory variable that is categorical on the what? On the response. What is it? What is the explanatory variable here? Machine. But machine is categorical, right? Machine has 3 levels, right? Why are you seeing 2 machines? Why are you seeing machine 2, machine 3? Because machine 1 is referenced. R has automatically coded that machine 1, okay, as 0. And that machine 1 is in the intercept. Now, if you take a look at this, a linear regression approach, okay, to do that. And what do you see? When I look at the effect of machine on the strength, if you look at the machine 2, if you look at the p-value associated with machine 2, machine 3, okay, that is greater than 0.05. What is it telling us? Machine is not significant. That is what it means. Now, this is using regression approach. But if I want to use ANCOVA approach, I told you, if I have data set, okay, I can use either regression or ANCOVA approach, except that ANCOVA approach are more appropriate with the experimental data or with the experimental study, while regression approach more appropriate with the observational study. Now, if you take a look at what I'm presenting to you now, this is a linear regression approach. But how am I going to do that with ANCOVA? I can also do that. Oh my God. Take a look at what I'm displaying now. This is doing that with analysis of variance. And we basically want to see whether we're going to take the same decision. If you go back to the regression, none of the machine is significant. Take a look at that. I mean, you don't talk about the intercept. We talk about the machines that appear in your output, machine 2, machine 3, since none of them is significant, what this is telling us is that machine does not have significant contribution to the strength. That is what this is telling us. Now let's look at what the analysis of variance is telling us. Oh my God, take a look at the degree of freedom for the machine. What do you see? 2. Okay, that is the reason why in the linear regression you are only seeing machine 2, machine 3. That's why the fact that you are comparing 3 machines. I told you the degree of freedom of that is 2 because we are comparing machine 3. Now, when you take a look at what if you look at the results that we have, there's something I want you to to consider. Let me explain this again so that you really understand. If you want to compare the results of linear regression with the analysis of variance, what do we compare? I'm going to say this again. If you want to compare the results of regression with the analysis of variance, what do we compare? We compare p-values. Which p-value? Oh my God. Take a look at this regression or output. There are 3 p-values. In fact, 4 p-values. Okay, if you look at the p-value for intercept, it's different from p-value for machine 2. It's different from p-value for machine 3. But if I want to compare, the p-value that I need here is a general p-value, which is the 0.04423. Can you see that? Can somebody confirm the 0.4423? The p-value, that p-value that you see is the one that tests the overall significance. Overall significance. Okay, the one that, there is in linear regression, there is individual p-value. If you want to talk about what is the contribution, okay, on individual level, but I'm talking about that p-value like the one I talked about adequacy, adequacy of the model. If I want to know how adequate, it's a linear regression model, I'm not going to talk about the individual p-value. I'm talking about the general p-value, which is 0.04423. That is 0.04423 should be the same when you run, analysis of variance. Let's see. Oh my God, take a look at that. Can you now see that they are the same? Do you see that? Do you see 0.04423 in the ANCOVA? What is the meaning of that? It means, the p-value here is less than 0.05, and therefore the effect of machine on the strength is significant. But when you take a look at this guy here, the general p-value is also saying the same. But individual p-value is not saying the same. The individual p-value here is going to tell us what is the significance of machine 2. Oh, what is the significance of machine 3? That is what the individual p-value is going to tell you. But the overall p-value is what I'm interested in. Now, what has happened here? We've looked at the effect of machine on the strength without putting into consideration any covariate. What have we done here? This is one-way analysis of variance. I'm going to say that again. What have we done here? This is one-way analysis of variance. But I want you to take a look at this. This result may be misleading. Why? It may be misleading if there exists a covariate that could influence the response. And we don't consider it now. And don't forget that covariate is diameter. Okay, now take a look at this now. We look at the relationship between the strength and that diameter, that covariate. Because you know why? Because the sum of square residual that you are seeing now, the mean square residual that you are seeing now, okay, may have an issue. just because we did not consider, we did not adjust, for the effect of a potential variable, that could have effect on the strength. I mean, on the response strength. Okay, now because of that, we plot, looking at the strength against the diameter, putting into consideration machine. Okay, we have that. Now I want to walk you through the ANCOVA model now, how the ANCOVA model work. Of course, the only reason why we basically need to tolerate an ANCOVA, a covariate in the model, is when that very covariate has a significant effect on the response. Okay, but we're going to start with a model. In the ANCOVA model, there's going to be an addition to ANOVA model. What is it? What is coming in? Beta 1 Sij. If I remove beta 1 Sij from the first model, I'm only going to have one way ANOVA, right? But if you look at the second form of that, okay, we're not just adding beta 1 Sij. We also are actually going to consider adjusting that. And how do we adjust that? You can see we have a beta 1 into parentheses Sij minus x bar dot dot, which means we're basically going to subtract the mean of that covariate from each and every data point. When we're doing that, we are actually adjusting for the covariate. I'm going to say that again. In statistical analysis, I think I'm going to say this. Do you know that correlation is not causation? You know that, right? Okay, the fact that if you say there's a relationship between two variables, that doesn't mean that one causes the other. Do you know why? We cannot. Okay, for instance, if I look at the relationship between the rate at which we consume ice cream and crime rate. I'm going to say that again. If I look at the relationship between the rate at which we consume ice cream, okay, the rate at which we consume ice cream, okay, ice cream, okay, and crime rates, right? So let's say we realize that there's a relationship. The relationship does not imply causation. That doesn't imply that ice cream will actually causes crime rate. No. Correlation does not imply causation. I'm going to write that for you to be able to see. But I want to bring out something there. Correlation, okay, does not imply causation. And I'm going to tell you why. The reason why correlation does not imply causation is because of what I call a third variable problem. Third variable problem. The third variable problem is the covariate. The third variable problem is the covariate. Okay, we need to be able to adjust for that. Okay, now I presented to you the ANCOVA model. What if in exam I ask you to write the ANCOVA model? That's what you can see now. And of course, the component of the ANCOVA model is what is defined. What is mu? Overall mean. What is alpha high? Fixed treatment effect, which is subject to, the summation alpha I equal to 0. Then the beta 1 is the regression coefficient that is coming in. Okay, and that regression coefficient, of course, is the one that will enable us to understand the relationship between the response and the covariate. Then, of course, you have the Sij, and of course, our error Eij must follow normal distribution with the mean 0 and the constant variance sigma squared. Okay, now, in a regression model, I know you've seen something like that before. Y equal to S beta plus the error. that is a way to write a multiple linear regression in a matrix form. And of course, the solution, the least square estimate of the parameter is actually the X transpose S, the inverse of that, and the S transpose Y. Of course, that is a layout, okay, where you're going to have Y, the observations you have, okay, you know, if you see Y1, Y11, Y12, we're going to have some observations that are for group 1. We're going to Y2, you know, where you see Y2 now, you're going to have some observations that are for group 2, and so on like that, depending on the numbers of groups that you have. And of course, you have a design matrix X. Of course, I walk you through this the other time. The first column, 1, 1, 1, 1 is for the constant. And of course, you have a beta, then you have the error. So take a look at that. Okay, now, the idea behind the ANCOVA is this. The model is called a parallel line modus or a separate intercept model due to the common slope. You remember the other time when we were working on the random effect model, I think I said we're actually going to have different intercepts, the same slope. Okay, that we're also going to have an assumption here where we're actually going to have separate intercept but the same slope. Now, you know, at times we may really want to test, you know, whether a treatment effect is significant or not. I want you to pay attention to the two models that you've seen on the board. The first model, Yij equal to mu plus alpha I plus beta I Sij minus x dot dot bar plus Eij, that is an ANCOVA model with covariate. Okay, ANCOVA model with covariate. But take a look at the second one. In the second one, we've already eliminated treatment alpha high. Okay, now if you take a look at these two models, if you want to know how significant is the treatment, you can compare these two models. Do you know that the second model is a special form of the first model? And why the first model is a general form of the second model? When alpha high equal to 0, you know what that means. You got a second model, which means the treatment doesn't have any effect. Okay, take a look at this. You know, I told you the other time, assumption that we have is that, you know, we're actually going to have different intercepts, but the same slope. Do you see the 3 lines? Each of the line represent machine 1, machine 2, machine 3. Don't forget, we actually want to compare the strength produced by 3 machines, putting into consideration diameter. What have we done here? This is a plot of the response variable against the factor, which is machine, and the covariate diameter. What can you see? Different intercepts, but the same slope. That is the assumption here. Different intercept, but the same slope. That is the assumption here. Okay, now, the very first thing we're going to do when we really want to justify ANCOVA is to first investigate whether there's a relationship between the response variable strength and the covariate diameter. It is only when this actually return a significant, result that we can actually, considering adjusting covariate, adjusting that diameter. So what am I just going to do? I'm just going to do a linear regression, right? A simple linear regression. Okay, let's see results. Okay. Oh my God. When you take a look at the results now, if you take a look at this now, I think we've done that before. Give me 1 second. Let me first see where we're looking at the effect of. Do we look at the effect of? Yeah, we've done that here. Do you see this? What are we doing here? We're looking at the effect. We want to see whether there's a relationship between response variable, strength, and the covariate, right? And the assumption, in the assumption, there must be relationship, right? Do you see the p-value for the diameter? What happened? It means the covariate is significant. Now, when it is significant, what are we going to do? We need to run an ANCOVA model. Now, and I want to walk you through how to run an ANCOVA model now. Now, this is running an ANCOVA model. Now, what do you see in an ANCOVA model? Strength is response. Diameter is a covariate. Machine is a factor. What do you see now? We are running an ANCOVA model now. We got a combination of the covariate and the machine. Okay, so take a look at that. Let's see results. Okay, if you take a look at the results, what happened now? Diameter is significant if you look at the p-value, right? Okay, and when you look at the machine, when you look at the linear regression, of course, you're basically going to see none of the machine is significant, right? Now, when you look at the ANOVA results, right, diameter is significant, but when you look at the machine is not significant, okay? But there's something I want you to see. When you look at the effects of the, the machine only, take a look at this. Can you see this? What happened? When you did not consider covariate, what happened? It's trying to tell us that what? Machine is significant. This could be misleading. In fact, not this could be misleading. This is misleading. You know why machine is significant here? Because you did not consider a potential, a variable that could influence, that can also influence the response. When an important variable is missing in your model will mislead. I'm going to say that again. When an important variable is missing in your model, then your model will mislead. What is missing here? Diameter. Okay? There's no, so we need to adjust for that. And in the end, what do you see? Machine is not significant. Machine is not significant after adjusting for the covariate diameter. That is what we mean. Now take a look at this guy here. Is there an improvement? Instead of me to use an ANCOVA, instead of me to use an ANOVA, and I use ANCOVA, using ANOVA is like, I'm only going to talk about effect of machine only on the strength. I'm not going to adjust for the covariate diameter. Okay. Now, using the ANCOVA now is when I look at the combination of the two. Now, what is gainful? Okay, if there's going to be any gain, where do you think we can have the gain? Oh my God, we're actually going to have the gain in the unexplained variation. What is the unexplained? The residual. Take a look at this now. When we consider only machine, what was the mean-square error? 17.167. When we now incorporate a relevant and important covariate in the name of a diameter, what happened to the mean-square error? We have a drastic reduction in the mean-square error. Let me tell you this: what we celebrate in statistical analysis is when there's a reduction in the mean-square error. That is what we celebrate. That means incorporating the covariate. When the covariate is significant, okay, we lead to drastic reduction in the mean-square error. That's what you are saying here. Any question on this? Any question? Now, the mean-square error was actually, for those of you who doesn't know where I picked the mean-square error from, okay, we actually, here you see 2.544. Where is the 2.544? Look at the mean-square error for residual in the ANOVA result. Then where do I see 17.167? That was what you conduct ANOVA on the machine only. I'm going to take you back to the machine only. Do you see that? 17.167. Okay. So which means we got a drastic reduction in the residual. And when you have a drastic reduction in the residual, then you have succeeded in improving the quality of a model. Okay, the next thing we're going to do, we now need to adjust. We've already seen the result. We cannot trust the current means of the groups. You know, the mean of the groups is like the mean of the strength for machine A, for machine B, for machine C need to be adjusted. Now that we have seen that covariate has significant effect, they need to be adjusted. What am I showing you in the first one? For the 1.4, for the 3.2, 36.0, they are the group means, you know, for the machine. Okay, then that of the diameter is what I'm giving now. Then the overall mean of the diameter is 24.133. So what needs to be done? We need to come here to perform the operation, okay, which I'm actually going to show you now. We call that covariate adjusted means. Our means need to be adjusted since the covariate is significant. And how can we actually do that? We got few ways to understand how, you know, how to do that. Number one, you run the model and estimate the means of each treatment when the covariate is set to X bar. Why are you doing that? Okay, because you realize that the covariate is significant. This is the first thing you're going to do. Take a look at that. We run a linear regression where we look at the effects of the diameter and the machine on the response. This is more or less like a multiple linear regression. You know, in a multiple linear regression, you have more than one explanatory variable. The first variable here is machine. Machine is categorical, has 3 levels. And the second variable here is the covariate that we call the diameter. Now, as you can see, we need to first get that. Okay, now from there, we can actually get equation for the parallel slopes. Don't forget, we want the slopes to be parallel. Okay, the parallel, they said, when the slope is parallel, oh my God, I remember what I did in high school. When we have a parallel slope, it means the slope are the same, right? Parallel, okay? But the intercept is not going to be the same. Now let's look at machine 1. How can we actually get for machine 1? Okay, I wanted to see what I'm using. yi bar dot adjusted equal y bar I dot minus beta cap, then in the parentheses, x bar I dot minus x bar dot dot. The x bar dot dot is the overall mean of the diameter. The x bar I dot is the, you know, the mean of the diameter, per group, okay, of the of the machine. Now, if I want to do that manually for machine 1, of course, it's just going to be 17.360, which is the intercept, plus, where do I get the 0.954? The 0.954 is the slope of the diameter multiplied by 24.133. That is the overall mean of the diameter. Overall mean, and what do I get for machine 1 now? 40.383. If I want to do for machine 2, it's going to be that same intercept plus the slope of machine 2. What is the slope of machine 2? As you can see in the output, 1.037. Why am I adding that? Because that's a positive. Okay, then I'm also going to say plus the 0.954 and so on like that. I will do the same for machine 3. That is doing that manually. If I want to do that using the R, I'm just going to follow that code. In the end, this is what I got. If you take a look at the first column, that is the sub means of the machine when you have not adjusted. But look at the last column, that is the adjusted means. Any question? This is where I'm going to stop. This is the final slide for today. Any question? If today's topic is very interesting, I need you to nod or you give a thumbs up. Is it very interesting? You sure? Okay. Is there any question before we go today? Any question? Make sure you stay safe and have a very good day. Bye for now, everyone.